last video, we saw that when V is a vector space over F, and you have a linear transformation T from V to V, then if we define x dot V to be given by T of V, this linear transformation applied to your vector, this gives the vector space V an F bracket X module structure. So the first thing that I want to do in this video is just give a couple of examples. So what happens if you take any vector space you want, and then T equals 0, the 0 linear transformation, where you send any vector to 0? Then how does a polynomial act on a vector V? Well, P of x dot V should be an t to the n plus a1t plus a0. We have seen how this is a linear transformation, and we apply this to V. But if T of V is 0, T squared of V is 0, this is going to give 0 plus 0 plus 0 plus 0 plus a0 dot V. So this just is the vector a0 dot V. So this a0 dot V comes from whatever the scalar multiplication of F is on your vector space V. So how does P act on a vector V? P acts on V by scaling by the constant coefficient of this polynomial. So none of the other coefficients matter at all. All right, let's take T to be the identity transformation that just sends every vector V to itself. So P of x dot V is now same thing, an t to the n plus a1t plus a0 acting on V, but t squared just is t. If t sends V to itself, a vector V to itself, then t squared is t of V, which is just t of V, which is just V. So every t to the n is also the identity transformation. So what is P of x dot V? It's an dot V plus an minus 1 dot V plus a1 dot V plus a0 dot V. And by the module vector space axioms here, this is an plus a1 plus a0 dot V. So how does a polynomial P act on a vector V? It scales that vector by the sum of the coefficients of the polynomial. Here's another example that comes from Dummett and Foote that I like quite a lot. Let's take V to be the affine n space over the field F. So its elements are like n tuples of field elements, x1 up through xn. And let's pick the linear transformation T to be the shift operator, where you take T of x1 up through xn, and you just shift everything over to the left by 1. So x1 disappears, and you get a 0 at the end. So you get x2, x3 up to xn in the n minus 1 coordinate, and then you get a 0. So we'll talk much more about bases for vector spaces a little bit later, but hopefully it's clear what I mean. This affine n space, f to the n, has standard basis vectors e1, 1, 0, 0, 0, e2, 0, 1, 0, 0, 0, up through en, 0, 0, 0, 1. What I mean, standard basis vectors, is every element in here can be written as a linear combination of these e1 up through en with coefficients in the field F in a unique way. Okay, so how does t to the k act on one of these standard basis vectors? Because if you know how it acts on a standard basis vector, then by the module axioms, you'll know how it acts on any linear combination of standard basis vectors, which will tell you how it acts on any element in f to the n. So tk e to the I, what does it do? Well, there's a 1 in the I position. And if you do t once, that 1 shifts over the left by 1. And if you do it twice, it shifts over the left by 2. So what happens when you do t k times? You shift over to the left by k. So this is ei minus k if I is bigger than k. If you have k spots over to the left that you can afford to shift. Otherwise, it's 0. So you should just think about what happens when you take like t1 of e1. You apply t here, and you get a 0. It shifts over. The 1 shifts over and disappears. So this tells you that when m is less than n, take this polynomial, am x to the m plus a1x plus a0. Applying the module axioms, this is like am dot t to the m acting on en plus am minus 1 dot t to the m minus 1 acting on en, and so on. And what happens? Well, like, what is a0 dot en? a0 dot en is just a0. We're just scaling the 1 in the last coordinate by a0. And what is a1 times t acting on en? Well, you just get a1 times en minus 1. It shifts over to the left, and you get an a1 here. So what you see when you work one term at a time and apply the module axioms is you get a bunch of zeros at the start, and am minus 1, am minus 2, down to a0 in the n position. So this tells you how any polynomial of degree less than n acts on en. Okay, so there's an exercise in dominant foot that you should think about for a minute, which says, okay, well, what if m is bigger than or equal to n? How does this polynomial act on, oh, this shouldn't say v, this should say en. Well, how did we get here? We just used the module axioms to see that we could work one term at a time. And once the degree is bigger than n, nothing interesting is happening. Like, what is Tn of En? It's 0, because n is less than or equal to n. So I won't write out all the details. I'll let you think about it. But that tells you what the answer is to this exercise. And if you know now how any polynomial acts on En, now you also know how any polynomial acts on En minus 1, En minus 2, just by like changing the names of these. Just doing exactly the same thing that we saw here, but starting one position over to the left. So this description gives you the action of any polynomial on any vector. So we're seeing what this f bracket x module structure is. You take any polynomial and you act on any vector in this affine n space, and we know what you get. The last thing I want to talk about in this video is how to think about this correspondence between f bracket x modules and a vector space together with a linear transformation. So we've already seen that if V is a vector space over a field F, and T is a linear transformation from V to V, then we see that V has an f bracket x module structure. So if you start with a vector space and a linear transformation, you get an f bracket x module structure. Well, what if you start with an f bracket x module? We've already seen that starting with an f bracket x module, you can show that it must be a vector space over the field F by looking at what happens with the degree 0 polynomials. And then you must have some action of x on this vector space. And that action must be a linear transformation. So if you just start with the f bracket x module structure, you can recover the linear transformation T by asking, what does x do to this vector space V? So x dot V is a linear transformation T from V to V. So what are we really saying? There's a bijection between the set of all f bracket x modules V, where, okay, so we're not just saying the set of underlying vector spaces V, we're saying f bracket x modules, we're keeping track of what is the f bracket x module structure on V, and pairs of a vector space over F and a linear transformation T from V to itself. How does this bijection work? Well, starting from an f bracket x module, first, the underlying module set is a vector space over F. We've seen why that's true. And where do you get this linear transformation T from? You get it from saying, what does x do to this vector space? So the element x acts on V by the linear transformation T. So from now on, every time that I think about an f bracket x module, I'm going to think about a vector space over F together with a linear transformation from V to itself.